We're going to do number 3 here. Number 3 is this setup of vectors. Now, what I asked you was for the length of this vector, vector 3, and I asked you the start position of the first vector, because I didn't give it to you. So, one of the things you got to realize is that, first question is, how many vectors do I really, if I'm asking for the beginning position of vector 1, how many vectors do I have? How many vectors are there? There are actually 4. Where's the 4th vector? Okay, that 4th vector, oh, that's pretty sneaky, goes from here to here.
Oh, I saw that one the first time.
Okay, so there's a vector, vector 4. Okay? So, here's the thing. These are displacement vectors, right? If I end where I begin, Sam Jeffries. If I end where I begin, what is my net displacement? 0. What's my net displacement in the x direction? What's the net displacement in the y direction? 0. No. If I end where I begin. 0, right? So that's my point. There's this extra piece here. So if we look at this, all right, and if I look at, let's look at V1, okay? If I have V1, I've got a vector here, okay, that goes from here to here and here to here, right? And I've got my vector and my vector. What's your vector, Victor? And I come down to here. Now, vector 2, right? Yeah. Vector 2, I've got a vector. I can break that vector into, oops. Okay, Yusuf, don't slam the door when you walk in. Thank you. Bring this vector. This vector 2 is made up of 2 vectors. Don't slam the door. Like this. So I have vector 2. Look. So for vector 1, I move over positive in the x and positive in the y. For vector 2, I move negative in the y and positive in the x. Vector 3, I move negative in the y and negative in the x, right? You guys see this? So really I have V3x, V3y. I have V2x and V2y. I have V1y and V1x. Okay?
Wait, what does the right one say?
V4. Let me erase that. And I've just called it V4. Oops, excuse me. Because V4, right? And it's really V4y, right? Okay? I'm going to call it V4y. So if I look at this to set this up, right, I have V1x plus V2x plus V3x plus V4x. And because I end where I begin, well, V4x is going to be what value, ultimately? 0. So I'm putting it in just to be clear, right? But it's going to, ultimately, they're going to add up to what?
0.
Right, because V1x is going to be positive, V2x is going to be positive, V3x is going to be negative. So when I add them all together, I'm going to get 0 meters. I can also do that for y. V1y plus V2y plus V3y plus V4y. And those are all going to equal what? 0 meters. Now, look, there's multiple ways of setting this up. You can literally do each one and go for it, but I'm just going to show you from a high level, just from a conceptual level, that we can add these subcomponent vectors up and you're going to add up to where we're going to end up. Now, look, normally, if I didn't end up where, by the way, if I didn't have V4, okay, V4y, what would
It would be positive.
Okay, well, let's say I was looking for V4y. Let's say I was looking for V4, right? I could say, look, you know what? Maybe rather than doing 0, I could say all those added together equal this. Right? Because ultimately, this v4x and v4y become my what? What vector? Because I didn't have v4 in there originally, right? What is v4? My what kind of vector? And what's that term for? Is R stand for? Everyone say it together. Resultant. The resultant vector, the summation, is the resultant vector. Now in this case, I'm calling it as v4x so we can v4 so we can understand that, right?
So
Okay?
v4x is the resultant.
No, v4, the vector v4 is the resultant.
Okay.
But v4 is made up of v4x and v4y. Do you guys see that?
Yeah.
Yes.
Right? So ultimately, these three vectors add up to my fourth vector, right? I can say I can say v1 vector plus v2 vector plus v3 vector equals my v4 vector. Right? But in the end, that v4 vector is made up of two subcomponents, the x and the y, just like we're doing. So it's two different ways of looking at the exact same problem. Does that make sense?
Which one's easier? Which one's the simpler way to look at it?
Don't think of it that way. Whatever makes sense for you. You got to think about whatever makes sense for you, because in the end, you have to know that if I didn't have v4, I'm going to end someplace relative to the beginning of v1. My v3 is going to end somewhere relative to v1. Well, that relative position is my resultant vector, right? Okay. And really, the resultant vector is actually what? Is it really the direction of v4 right now? Is it actually what?
The magnitude.
No. Think about the direction. Normally, if I have my resultant vector, here's my first vector, here's my second vector. Which direction where's my arrow on the resultant vector? To the top right, right? Yeah. But notice the resultant vector rx and ry, right, goes from the beginning to the end.
Oh, yeah.
So typically, if I was looking at the resultant vector in this case would be what direction? For this one here. If I didn't have v4, let's say I didn't have v4, okay? Where's my resultant vector go from? From the beginning to the end. So which way does it go?
It goes.
Where's the begin? Where's my beginning? Where's my beginning?
0, 0.
Wait. Beginning of v1. Where's the end? The end of v3.
Oh, it started out.
Yeah. So right. So it goes south. My resultant vector is actually opposite of v4. Do you guys see that?
Yeah.
And so that's all you have to work. And by the way, when I move this v4x and y over, what am I really dealing with? I'm really dealing with a sign change. It really should be negative, right? But if it was resultant, I don't trying to confuse you, but just keep in mind that, look, you can do it two ways. One, I can feel like where my resultant vector is and know that I'm opposite of where I am, or I can say, hey, look, here's a vector. Oops, here's a vector v4 that could complete it. You can look at either way. You just have to be careful of your signs. If I ask you for the resultant vector would be pointing, going from the beginning to the end. In this case, I just did a normal vector up, finishing this off so that I knew where I was. A little confusing, but don't get too caught up on it. But again, the point is you've got multiple ways of doing this. So I'm going to put this back over here because I like this idea of saying, hey, look, I'm going to add up these vectors and get 0. Does that make sense? So it should be 3 different ways of looking at the same thing. Okay? So now you've got that, you have to start to say, well, I got to figure out what all my subcomponents are. So can I figure out immediately the v1x and v1y subcomponents? Could I figure those out pretty quick?
Yes.
How do I? What numbers am I using? What things am I using to figure out v1x and v1y?
What things?
What am I using in order to figure out how would I? SOHCAHTOA, I'm going to use what?
Like specifically?
Yeah, but what for v1? What things am I going to? What things am I going to use? Sine, but I'm also going to use the angle, 30 degrees, right, and the length. Okay, so I have a 5.8 and a 30 degrees, right? I have my lengths of V2. I don't have my length of V3, right? I don't have V3 length, so it's going to be tough to find V3. But I also can't necessarily figure out V2y and V2x yet, can I? Because what do I need to get? I need to figure out some sort of angle, right?
Yeah.
Okay. So how do we figure some of that out? How do we figure some of that out?
Solve for V1, right?
Well, before let's start to throw some angles in here. How do we figure out what any of these angles are?
Which are you talking about in V2?
Let's talk about for V2. How do I get some angles for V2? Let's think about how to do that. How can I possibly do that?
It's a right triangle, right?
Well, it's a right triangle here, but what's this angle? What's this angle?
You know the total, you got the top one.
How do you know the top one?
It's 25 because the triangle above it is 30, 65.
Okay,
Wait,
that's 65, but you don't know that's 90.
so that's an 85 degree.
How do you know that's 85? This is 85, but how do you know that's 85? Okay, this is good. This is good. This is good thought process.
Oh, because of the quadrilateral.
Well-
It's a quadrilateral.
From here, okay, so you have what? You've got in the quadrilateral form.
With 115, 85, 90, which makes the other one 70. The bottom left.
This one makes this what?
70.
Okay. That's 70. This is 80. 70. That's 90 and 100. 90 and 30 is 110.
And so
And then you can work that way. So you can start to do quadrilaterals, right? Another option is if I said this. This is 90 degrees from the green to here, right? Okay, so that's 90 degrees. So now 90 degrees. Oh wait, didn't I do this right? Oh, I did this.
it goes from 85.
Did you
But
just
that 85 is
85 to 90. Hold on. 85. Oh, I did this. I keep doing this. There's a way of doing this, and I keep forgetting how to do this. Sorry, guys. That's 85. That's 90. That's 90. There's a way to figure out this angle here. This angle here. Oops.
Oh,
From here to here, because we know that this is 90.
Oh, it's from 115, the angle 115. If you extend,
Oh yeah, you can extend this out, and this is
if you extend V1 again,
yeah. This is going to be what now?
that's the
Right. This okay. Yeah. If that's 115. This is 65, right? So that means this is 65. That's the way to do it. My bad. So you could say, okay, here, this is 115. This is 65, and therefore that's got to be 65, right? Everyone with me on that?
Yeah.
There's like a million ways to do it. I always forget. There's always different ways. So that's 65, which means if that's 65, what's this angle?
Which angle?
This one up here. 25 degrees, right?
Yes.
Okay. And if that's 65, what's this angle here? Also 25 degrees, right? Oh, no, take that back. No, take that back. 65. This is 20 degrees.
Yeah.
This is 20 degrees. And that means this is 20 degrees, right? So now I've got this angle, and this angle. I can start to do that. And this is actually the fun part of the geometry, and figure those angles out, right? So, and I just keep doing that.
I feel like that's the meat and vegetables part. And then you get the fun part.
Yeah, so did you see my comment, by the way? Did you see my comment on your blog?
I've heard about it, but I haven't read it. I've yet to read it. I heard it was funny though.
Well, how did you hear about it?
Apparently.
Yeah, the quote of the day, I can make a quesadilla.
Oh yeah.
She's like, Miss Wisdom is like, can you cook?
I said that.
She goes, can you cook? And you go, I can cook. I can make a quesadilla. Which I thought was hilarious. I don't know, that was funny. All right, so now I've got some angles, and these angles I can do what, guys? What can I do with these angles? Okay, so now I can figure out these. I can figure out these lengths, can't I? All these different lengths, right? Okay, so let's figure this out. So let's figure out how do I figure out v1x? What's v1x? v1x is equal to what? Let's do the quick piece here. What's v1x?
It's sine 30 equals adjacent.
Wait. Is it, if it's v1x, the quick is, if v1x, remember, here's the thing. If I've got a triangle like this, okay, if I've got a vector, and I have vx and vy, right? If it's set up in this fashion, guys, here's a shortcut, but you got to be careful about the setup. Vx is always going to be equal to v times the cosine of theta. Vy is always going to be equal to v times the sine of theta. And this comes from your unit circle, right? But it's set up as long as your triangle is set up with your theta in the bottom left corner, and to the right of that is your 90 degree. Does everyone see that?
Yeah.
So in this case, v1x is equal to v1 times the what? Cosine of theta, right? So that means v1x is equal to times the cosine of what? 30 degrees. Cool? Let's do all the x's together here. Let's do v2x is equal to what? Which one's v2x? Bottom one. So
it's going to be v2 sine theta?
well, let's look at the, okay, why is it sine theta? Right, because the triangle's turned, right? Right? You guys see that?
Yeah.
Can you open this door? Okay, so v2 times the sine, thank you, of what? What angle?
65.
No. If you're doing this, if it's v2 sine, it's not 30. What is it? No, up here, look. 25 degrees. You guys see this?
Oh, yeah.
Right? Because it's like this,
Oh, yes.
like this, and like this, where this is your v2, this is v2y and v2x. But since your theta is up here, it's like I took this and rotated it, right? It's like this guy, where this is theta, this is my v2, and this is my v2y, and this is my v2x. Do you guys see that?
So you do the same thing with the v2x as v2y, but you just switch cosine and sine.
Because look, regardless of what this is, this could be v2 pink elephant. In this scenario, this length right here is v2 times the sine of theta. This is v2 times the cosine of theta. Regardless of its x and y. You see that?
Yeah.
Whatever this side is, that's what it is. Now I could, again, call it purple dinosaur, pink elephant, or v2x, or v2y. It really depends. But that's why I say with that whole shortcut, v1x equals v1 cosine theta, and comes great responsibility, because you need to be very careful about the rotation of your triangles. Does that make sense? So be careful about this. This is why I did this. All right? Clear?
Crystal.
Beautiful. Look at that. Yeah, buddy. Are we clear? Crystal. All right. So there's that. So now what is V2? Now what is here? Shh. Okay. Do we know what V3X is from angle stuff? Do we know what V3X is? Well, we'd have to know our angle and our magnitude of V3, but do we know the magnitude of V3? No. Okay, so we don't know what V3 is just yet. Okay? But let's look at this top equation. Let's look at this top equation. I'm going to get a value for this, and V2x is going to equal 5.8 times the sine of 25 degrees, right? Everyone there with me?
It's not 5.8.
You're right. I'm sorry. It's not 5.8. It's 10.3. Excuse me.
V2 trip.
10.3. All right? I'm going to get values, right? So I'm going to get a value for, everyone look up here, V1x. I'm getting a value for V2x. I'm still looking for V3y, but what's V4x? What's V4x, guys? 0. So now what do I have?
You can solve for V3.
I can solve for V3x, and that makes graphical sense, right? V3x is just the opposite of V1x plus V2x, right? Does that make sense?
That makes sense.
Okay. So I can figure that out, right? I'm not going to go through the math. You guys can do that. Because V4, the x component of V4, is just purely vertical, so there's no x component.
Oh, right.
Right?
Right.
Okay. If I had V4x, then I'd have to give you something. Otherwise, you'd have two unknowns, and you'd be
Right.
up a creek there, right?
I got it.
So V1y, let's look at V1y. Let's look at V1y. What's V1y equals, guys? V1y equals what? Give me the upper level equation. Equals what? Come on, guys. V1 sine theta. Give me the upper level equation first. Then V1y equals, what's my V1 value? Times the sine of? Okay. You need to do this step. You've got to do this front step. Why do you have to do this front step?
To show the thought process.
So that I know what you are thinking. I'm sorry, I know this is tough. You guys are in class. The whole purpose of this is to make sure I understand you understand. When you're out in the real world, then you can do it however you want. You get it. But I want to make sure that we're clear on this. And that way you get full credit. All right. And by the way, I've been doing this for how many ever years, and I still have to go and do this. I still have to sometimes go through and do this, right? Because I forget. I got to rederive. Okay, so there's that one value there, right? What's V1? What's V2y? What's V2y, guys? V2y, upper level equation. V2y is?
10 point
Upper level equation.
these 2 times cosine.
Beautiful. So V2y is equal to 10.3 times the cosine of 25 degrees. So there's another value. Okay? Okay. Now the question is, how do I figure out V3y? Because right now I have, if I go back to my upper level equation, I say, okay, I have the value for V1y, I have a value for V2y, I don't know V3y, and I definitely don't know V4y. Yes, sir?
Don't you have V3x now?
I do, and what can I do with that?
You can use it and the angle to find V3y.
I can do two things. I can either use an angle in V3x to find V3, or I can use it to find V3y. Right? So V3y is equal to what? Well, let's do it a little more trigonometrically, right? I have to. There's no real. I got to make sure I'm going. So it's gonna. If I'm using for 20 degrees at theta, what am I going to be? I have V3x. Oh, I'm looking for V3x, right? Oh, I know. Let's figure. Someone calculate what V3x is really fast. Someone calculate V3x. What is this number right here? So what's 5.8 cosine 30? 5.8. Let's see. 5.8.
5.8 cosine 30.
So 30 cosine times 5.8 is 5.03.
No.
022. Excuse me. Yep. Meters. That's what you said. You did say that was good, right? And then it's 25 degrees sine times 10.3 is what? 4.31. 4.31 meters, right? So that means that V3x is really equal to the opposite of those two together, right? So it's 4.31 plus 5.02 is 9.33. So V3x is equal to the negative, what, 9.33.
Did you do V2y?
I did V2x and V2. I'm just trying to figure out what V3x is at the moment. Does that make sense?
Yeah.
Okay. And so now I can say, well, V3x. So if I have V3x and I'm looking for V3y, how do I do that? What trigonometric function am I going to use? Beautiful. So the tangent of theta is equal to my v3y over v3x. So v3y is equal to v3x times the tan of theta. And now I know both of those numbers. v3y is going to equal to negative 9.33 meters times my tangent of 20 degrees, and I'll get that number. Does that make sense? Okay. That kind of gives us a position on how to do that problem. Now, I'm not going to go through the rest of the math. You guys can do that on your own, right? You've got pretty much set it up. Now, because if I want to figure out the length of V3, I can figure that out, right? If I want to know the V4y, I'll start to plug stuff in because there's V3y right there. Now I've got it. And then I'm looking for that. Does that make sense? Beautiful. This is how this, guys, this is how this works for every single problem.